Thank you, Josie, for the invitation. It's always a pleasure to speak here at this amazing conference. And also thank you for organizing that, all the people involved, Ars and Veronica, Humia, yourself, and many other people to make this actually happen. Thank you for allowing me to talk a little bit about different things, because it's great to see so many young people here as well, young researchers who are excited about morphological computation and embodied intelligence. And I think it's a good idea also to discuss a little bit the direction of the field could go or should go. And as I mentioned, I've been in the game of morphological computation for a while now, and discussing with my group and my young researchers in my group, I think there are a few opportunities that I would like to highlight today. And maybe it's also some, food for thoughts for our discussion panel later on. Now, obviously, this list is not going to be exhaustive. 10 minutes is a very little amount of time for doing that, but that's okay. But also, it's very biased. So I've chosen these opportunities because I think these are the ones who have a lot of potential, but are currently a little bit underexplored. So to let you know how we're thinking about morphological computation, I just bring you this picture, which is well known in the community. I simplified it a little bit, just to explain what my research group is doing with respect to understanding how we can build better bodies in order to get better robots. And that's the way we understand morphological computation, very specific in the context of robotics, obviously inspired by a lot of biological systems, but at the end, we want to get better robots. And there are two aspects to that. One is this side where we think about, can we build better morphologies in such a way that it facilitates and improves the interaction with the environment. So this could be something to improve the entanglement with the environment, to get more energy efficient systems, or better systems with respect to robustness or resilience. But it also includes everything about sensing, because we sense the environment in the robot as well through a morphological structure. And maybe this morphology can help us to get better information out of a noisy and uncertain environment. And the other part of the coin is this side, where we think about how can we build better bodies and morphologies in order to facilitate learning and control. Can the body help us to have better, more robust controllers, but also accelerate and improve learning overall? Now, what are the opportunities that I would like to point out today? The first one is I call morphological computation and machine learning. And by that, I don't mean that we should use more machine learning in order to get better morphologies. People are doing that already, and I think it's a good tool to use. But I think morphological computation and its concepts can actually provide a lot of interesting input for the machine learning community. So if you look at the robots, you can also think it as a more abstract machine learning approach system. So I would suggest that the first layer of a more complex machine learning approach could be actually implemented as a physical layer. And this is not something that is completely made up, because if you look at convolutional networks, that is directly inspired by the biological system, where you have this kind of local connections that help the visual kind of system in the human body, for example, to detect edges. So we could, for example, think about morphologies that help us to expand or extract or exploit this kind of local communities of information bots that we have by dynamically coupling local morphologies. But we could even think even beyond that. We could think about not just in the spatial kind of dimension, but also what about frequency? What about time? Are there things that we can think about dynamical morphologies where they actually have neighboring kind of morphologies in the dynamic space, in the frequency space, and therefore extract information and features for a machine learning approach? Now, the machine learning side, the more abstract one, could also feedback to the morphological layer and even make changes. So we have an adaptive morphology to improve over time, for example, the extraction of information. So I think the feature extraction side is something where morphology and morphological computation can play a very crucial role in machine learning community. And also, I think if you implement the first layer as a physical system, you by definition get a real-time kind of response. And it's also very likely to be very energy efficient, because it's mostly passive systems that we're talking about. So the energy comes from the information from the outside, be it a chemical gradient, be it a physical force, electromagnetic kind of forces, and so on. So you can have actually quite energy efficient systems, and a lot of the work can be offloaded to the morphology. And finally, I think morphological computation and having a morphological layer connected to more abstract machine learning approaches would be a really good fit for neuromorphic computation. In nature, we see that already happening, and I think it's almost a natural marriage, and it's something that could be explored there as well. Now, the second opportunity, I think, that has been explored previously, but somehow stopped, and I'm not sure why, because I think there's still a lot of things that we can actually learn. The morphological space, the physical space, is actually something that can provide very useful constraints for learning. So if you look at the classical robot, like an Asimo robot, and you want to learn a picking challenge, and you would have to control all degrees of freedom of your robot arm. If you look at the actual signal and having this position, which is close maybe to the object that you want to pick, and this position, there's no real difference. It's just a mathematical vector. So there's no weight that tells us, okay, this one is better than this there. However, if you look at a biological system, you get a lot of constraints. For me, it's really hard to do that because there are these kind of constraints in my body that makes it hard for me, and I need more energy to go back there. So naturally, I'll explore much more in this direction in order to do something. In addition, sensory coupling is also really interesting. And you see that in babies, they move their hands around in front of the face because they enjoy really this kind of sensory stimulation. They don't do it on the sides. So it helps also to have this coupling with the morphology, where the sensors are positioned, in order to help the learning algorithm to find a space where it should look first. But you also can think about more general, like if that's your big space of learning, right? You can start with a very small one, which makes it much easier to find an optimal solution. And then over time, you can extend it and make it bigger. So you have to think about how we can have this kind of controlled extension of our search space in order to help our learning along. And one very simple way, and people have done it before, is to going from static solutions to more dynamic solutions. And I think humans do that to a certain sense as well. If you learn a new sport and you swing, you're very stiff, right? You reduce almost your search space, and then we get better and you're actually more relaxed and more dynamic. You can also think about growing systems. And there has been done some work, for example, by Josh Bongard. We did as well, both in simulations, where we saw that if you have a small system and you grow it into more complex ones, and then you use or reuse this previous kind of controller policies, you actually kind of take advantage of expanding over time and get actually much more robust controllers, but also faster ways to find perfect controllers for your system. So it's all about this area, how to find morphological features that is worth to explore in order to change, in order to help the learning, for making it faster and also more robust. Now, the third opportunity is what I call moving the line. Now, when we talk about morphological computation, there's this kind of concept that you say, well, the kind of line between the control and what is controlled is a little bit blurred, but actually there are some things you can clearly say that happens in the body and other things that happen clearly in the brain. And there's a whole discussion about what should be outsourced to the body and what should be actually pertained in the brain. And while there is some kind of these examples in extreme science, for example, if you do long-term planning, you want to go into the digital kind of realm. But if you want to have some kind of real-time energy efficient kind of responses, you might want to implement it in morphology. But it's this huge gray area in between that we not really know where to draw a line, should we draw a line, but there is some kind of separation going on. But it's very often assumed that this separation is fixed, right? Because we're thinking very often in conventional robotic terms still. Well, we build a system that is meant to do very specific tasks and all the flexibilities in the brain and not so much in the body. So you could think about a task and you say, well, at the beginning, when I start out doing this task, there's a lot of computational work that happens in my brain and maybe a little in the body. But if you have mechanisms in place to translate your understanding of the problem by interacting more and more with that, and you have some mechanisms, you may be able to outsource that to changes in the morphology. So the morphology can take more of the work, can be more energy efficient, for example, and the actual controller can be reduced. So this arrow is here again very important. What kind of mechanisms do we have to think about what kind of degrees of freedom we have to change in order to get a meaningful translation of mental tasks into a body task. So this could be like an abstract version of a muscle memory. So it's in the conscious realm, and then it goes down into the morphological realm. And then, of course, it goes the other way around as well. If there's a big surprise now because the desk has changed or the environment has changed, then we have to go back and then be more brain heavy again and think about new ways to actually outsource this new way of working with the new environmental conditions into different changes of the morphology. One of the key problems or things that are important here is the quantification, right? You want to be able to quantify that this actually happens. And there's been done some work in quantification. So Daniel Bolani is working on empowerment, for example. Kian Sayedi and I, they're working or have been working on very cool quantification approaches. So there's some work that can be used, but there's still much more work to be done. Now, the fourth and the last one is what I call growing machines, because if we look at the body in morphological computation, there's some kind of functionality in there. That's the basic assumption. Now, this also means if we change the body, we actually change not just in size, but also we are growing and we're changing the underlying functionality. The same is actually true for healing, right? You're not just healing a specific body part or some tendons, but actually you're healing or you want to heal the underlying functionality. But this also offers a possibility for programming and reprogramming the body. So imagine you have this kind of blob of some kind of soft material, then you would have rather a design space than any kind of specific solution for a specific task, which is very common to conventional robotics, but rather to say it's this blob of potentiality, right? You need some soft passive tissue, so you get some intelligent materials in the smart materials. Which ones? That's the big question. But you can imagine if this kind of blob interacts with the environment, maybe in water flow or it bumps into something. So it means locally it experiences some kind of interaction with the environment, and locally the smart material is able to change and translate this experience into a morphological exchange. It could be change of stiffness, pH value, electromagnetical properties, and so on. And if you have an intelligent enough system, you might be able to translate different types of stimuli into different kind of changes, or maybe even the same, but if it's maybe a force that is at very low frequency, it will be translated differently than at high frequency, for example. Now, this means that suddenly you have to think about a design space that allows different possible solutions rather than just one specific solution. And growing is definitely something that could help us. One way to think about is also design through stimulation. So instead of having a design and then assemble it, actually think about we have this potential and then we stimulate it in a very precise way, in such a way that it actually converges into a morphology that we want to have. And we're currently exploring that, for example, with stem cells, which can then, depending on the mechanical stimulation, become cartilage or bone cells, for example. So you can actually, the way you stimulate it, you get different kind of morphologies. Another thing that we're currently doing is we're using protocells as well, going in the same kind of direction. Okay, so these are 4 opportunities. There are many, many more, obviously. But I think these are the ones would have a huge impact on the community. And there are some low-hanging fruits, some big questions in there as well, some huge challenges. But I think it's worth to have a look at those. And these are the people in my group who are inspiring all these things that we're thinking. So it's not my ideas alone. These are ideas that come in mostly from the young people who are very clever and thinking about this very deeply. And a lot of discussions, these kinds of ideas are popping up. So thank you to them. And if you want to get in touch with me, here is my Twitter account, my email address, now webpage, morphologicalfoundation.org. Thank you very much.
Thank you so much, Helmut. That gives us a lot of really excellent starting points for the panel discussion. So thank you very much.